In section 2.1, we're going to look at all the different kinds of numbers and the number sets, and also we're going to look at square roots. First, let's define what square roots are. A square root is the opposite of squaring a number. The symbol you use for a square root looks like this, kind of like a check mark. So if I said the square root of 9, it would look like that. And it's always good to know the first few numbers that are perfect squares. What a perfect square is when you take a number and you square it, that answer is a perfect square. So for example, if I square 1, 1 times 1 is 1. So 1 is a perfect square. If I square 2, so 2 times 2 is 4. So 4 is a perfect square. 3 times 3 is 9. So 9 is a perfect square. 4 times 4, 4 squared is 16. 16 is a perfect square. 5 times 5 is 25. 6 times 6 is 36. 7 times 7 is 49. 8 times 8 is 64. 9 times 9 is 81. 10 times 10 is 100. 11 times 11 is 121. 12 times 12 is 144. 13 times 13 is 169. 14 times 14 is 196. And 15 times 15 is 225. Now, it's always good to know the perfect squares through 15, so through 225. Not that there aren't any perfect squares after this. There's still 16 times 16, 17 times 17, so on and so forth. But it's always good to know at least 1 through 15, they're perfect squares. Now let's look into how to actually work with square roots. So in all of these examples, we are going to approximate the square root to the nearest integer. So an integer is a positive or negative whole number. And so when we're approximating it, that means it is not an exact answer. We're just going to get an answer that's almost equivalent to the real answer. So when we look at number 1, we have the square root of 27. The way you do this is what you're going to look at or look for are the two perfect squares that 27 straddles. So 27, the perfect square that is less than it would be 25, 5 times 5. And then the perfect square that's bigger than it would be 36. 27 sits in between those two. It is 2 units away from 25 and 9 units away from 36. So you would approximate that the square root of 27 would be closer to the square root of 25 than to the square root of 36. So we would say the square root of 27 would be about 5, since 27 is so close to 25 and the square root of 25 is 5. Moving on to number 2, we have negative square root of 78. So I'm going to think of this as negative 1 times the square root of 78. Instead of just negative square root of 78, I'm going to look at it as negative 1 times the square root of 78. So I'm actually going to deal with that negative 1 last. Let's then look at what the square root of 78 is. We're going to approximate that. So let's look at the two square roots that 78 is in between. The one lower than it would be 64. And the one bigger than it would be 81. So 78 would actually sit closer to 81 than it would 64. 78 is 14 units away from 64, but only 3 units away from 81. So you would think that the square root of 78 would be closer to the square root of 81 than the square root of 64. Since the square root of 81 is 9, we would think that the square root of 78 would be almost 9. So we're going to say that is about negative 1 times 9, since the square root of 78 is almost 9. So our final answer would be about negative 9, because remember we were separating that negative sign from the square root of 78 and thinking it as negative 1 times the square root of 78. So our final answer would be found by taking negative 1 times about 9. So our answer would be about negative 9. Now let's look at number 3, the square root of negative 65. Really think about what a square root means. A square root means what number times itself gives me the number underneath the square root symbol. So if you think about it, if I ever take a positive times another positive number, I would always get a positive answer. If I took a negative times a negative, I always get a positive answer. So if we're trying to find a number times itself that gives us negative 65, that's impossible. There's no way to take a number times itself and get a negative answer. If the number was positive, a positive times a positive is a positive. If the number was negative, a negative times a negative is positive. So in this case, our answer is no solution, because again, you cannot take the square root of a negative number, since there is no number times itself that would give you a negative answer. Math is like its own language with all of its different symbols and terms that all mean something within the math language. Within the math language, there are different types of numbers, and these are actually number sets. So remember, when we're talking about sets of numbers, we use the braces, just like when we talked about range in the last chapter. So the first set of numbers that we're going to talk about are the natural numbers. Another name for the natural numbers is the counting numbers. So if you think about when you count, you start with 1. So the natural numbers would look like this: 1, 2, 3, 4, and then we couldn't just keep counting forever. So we use the dot, dot, dot in order to signify that we're going to continue that pattern forever. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, so on and so forth, forever and ever. We could not write all the numbers because they never end. The symbol for natural numbers is a double bar N. So basically you just draw an N and then you put an extra little tail on it. So that would be the natural number set. The next set are the whole numbers. Basically the whole numbers are the natural numbers, but this time we're including 0. So again, it's a set of numbers, so we use the brace. 0, 1, 2, 3, dot, 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 so on and so forth. Again, with that same pattern forever and ever. There really is no universally accepted symbol for whole numbers. You would think maybe it's like a W with an extra little bar in it, but when we're talking about the whole numbers, we really just talk about the whole numbers instead of using a symbol. The next set of numbers are the integers. The integers are basically the whole numbers and their negatives. So when we write it, since we're starting with all the negative numbers, we're actually going to start with a dot, 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 and then we'll say -3, -2, -1, 0, 1, 2, 3, and again, we're going to continue that pattern forever and ever. So the dot, dot, dot in the beginning means we're going to keep going into bigger and bigger negative numbers, and the dot, dot, dot at the end means we're going to keep going bigger and bigger into the positive numbers. The symbol for the integers actually is a Z. It's a double bar Z. It looks like this. You kind of draw a 7 and then an upside down 7. That would be a double bar Z. The next set of numbers are the rational numbers, and there's really no way to write these numbers as a set of numbers. There's only a way to define them. A rational number is any number that can be written as a fraction. The symbol for the rational numbers is actually a double bar Q, and I've seen it written 2 ways. You can draw a Q like this with 2 little tails, or you can draw a Q with a regular tail and then you just kind of draw a line right there. Either way, they both mean rational numbers. Kind of like rational numbers, irrational numbers, you can't really write them as a set of numbers, you can only define them. So rational numbers are any number that cannot be written as a fraction. If you think about the prefix "ir," that means not. So if rational numbers are numbers that can be written as fractions, irrational numbers would be any numbers that cannot be written as a fraction. So we're thinking about things like the square root of 78. If you looked at what actually the square root of 78 is from the previous examples, it's a number that goes on forever and ever, but it cannot be written as a fraction. Pi would be a perfect example of an irrational number. Pi cannot be written as a fraction, and it goes on forever and ever without end and without repeating. Rational numbers can repeat. Irrationals cannot. The symbol for irrational numbers is actually just a double bar I, so it looks something like this, kind of like a Roman numeral 2, but it's a double bar I. The real numbers are any numbers that you can think of. Any number on the face of the planet that you can think of are part of the real number set. So any of the natural numbers are real numbers, any of the whole numbers are real numbers, integers are real numbers, rational numbers are real numbers, irrational numbers are real numbers. The symbol for real numbers is a double bar R, and it looks just like that. You just basically draw 2 lines and then connect them to make it look like an R. So that's the real number set, and again, it encompasses all of the number sets. And speaking of encompassing, if you look at all of these different number sets, you can find most of the number sets within others. For example, you can find the natural numbers, the counting numbers, within the whole numbers, because remember, the whole numbers is basically what the natural numbers are, just we're including the number 0. So within the whole numbers, you find the natural numbers. Within the integers, you can find the whole numbers. So the whole numbers are 0, 1, 2, 3, and look, 0, 1, 2, 3. So the whole numbers are part of the integers. Integers can be written as fractions, so any of the integers you can put over 1, so they're rational numbers. And then when we combine the rational numbers with the irrational numbers, we have the real numbers. So all of these number sets fit inside of all of the real number set. So in the next slide, you'll see that relationship. So what we have here is a diagram representing the real number system. Thinking back to our last slide, the smallest set of numbers were the natural numbers, the counting numbers, and those started with just 1, 2, 3, 4, 5, so on and so forth. So our smallest set were the natural numbers, double bar N, and again, those would be numbers like 1, 2, 3, dot, dot, dot. The natural numbers fall within the whole number set. So it's kind of like a Venn diagram that we're making here. So the whole numbers are a slightly bigger set of numbers, and the natural numbers live inside of those. Now remember, the only difference between the natural number set and the whole number set is that the whole number set includes 0. Otherwise, they're exactly the same set of numbers, just the whole numbers also include 0. The whole numbers fall within the set of integers. So remember, the symbol for integers is that double bar Z, which remember is just like drawing a 7 with an upside down 7. The integers are numbers that are the positive and negative whole numbers. So we have the dot, 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 start with -3, -2, -1, 0, 1, 2, 3, dot, 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 because it goes on forever and ever. The integers fall within the rational number set, because remember, integers can be written as fractions by putting a 1 under them. And the definition of rational numbers are any numbers that can be written as a fraction. So remember, the symbol for rational numbers is the double bar Q, which can look like this or like this. Now, separate from the rational numbers are the irrational numbers. So the irrational numbers are a completely different set of numbers. That's why they have this box on the right all to themselves. The irrational numbers are any numbers that cannot be written as fractions. So we're thinking numbers like pi, or numbers like the square root of 67 or the square root of 13. None of those numbers can be written as fractions. They would be non-terminating, non-repeating decimals. Rational numbers combined with irrational numbers all fall within the real number set. So any number you can ever think of, so like numbers that can be written as fractions, numbers that are just whole numbers, negative whole numbers, numbers like pi that go on forever and ever and never repeat, all of those fall within the real number set. And oddly enough, there are other sets of numbers. There's a set of numbers called the complex number set, and those you get from taking the square root of a negative number, but it's something that you'll talk about when you get into Algebra 2. So again, this is just a diagram showing the different relationships between the different sets of numbers that all fall within the real number system. Make sure you write down any questions that you have over this section and come to class with those questions ready to go so we can get them covered before we move on to the next section.